I would just ask each mentor to give a brief introduction so I can say everyone's name properly, if nothing else. So Oksana, I think you're first then.
Yeah, so it was pretty cool summer for me and Keisuke. Keisuke was working together with me, Brian, Can, but they didn't manage to join because probably for them it's a bit too early, on trying to understand how could be beneficial preconditioners, particularly Bitshuffle, applied to different root compression algorithms, and particularly we were looking into improving some corner cases for LZ4 and to verify as well, since LZ4 and Z standard is very close, to check if we could even benefit from higher compression ratio. So he did an amazing job. I think particularly was very nice that we stayed on absolutely like different time zones, and still Keisuke managed to always communicate results, participate in root IO meetings in very uncomfortable times. So yeah, please show us a bit more about your work.
Yeah. Can you see my slide?
Yes.
Yeah, so I'd like to start my presentation. My name is Keisuke Kamahori. I'm a sophomore at the University of Tokyo, and this summer I have been working on the preconditioner of compression algorithms of root as a GSoC student. To summarize what I have done this summer, I have added a new compression algorithm to the root file system. I integrated LZ4BS, namely LZ4 algorithms along with a preconditioner Bitshuffle. Bitshuffle is a preconditioner of compression algorithms. Bitshuffle doesn't compress data in itself, but combined with some other algorithms like LZ4, it can improve the performance of compression and decompression. These diagrams illustrate basically what LZ4BS is doing. When you compress some data, firstly, Bitshuffle manipulates the input bytes according to a predetermined algorithms, and then apply LZ4BS to get compressed data. On the other hand, when you decompress some data, firstly apply LZ4 decompression, and then do bit unshuffling to get the original data. Bitshuffle transposes input binary data as shown in this illustration. When Bitshuffle gets the data on the left, the input is transposed to the data on the right. Bitshuffle is known to improve compression performance, that is compressed size and decompression speed, when the input is typed binary data or when adjacent bytes are highly correlated. And next, I'd explain the implementation of Bitshuffle in root. First, Bitshuffle will be applied only when the size of source data is the multiple of 4, in order for Bitshuffle to work properly. After that, we take comparison approach to use the full potential of Bitshuffle, which means we try to compress input data with both LZ4 and LZ4BS, and then choose better one. You may wonder this approach needs much computation and compression speed can become very bad. However, it was not the case. I'll explain about it in later slides. Moreover, we support vectorization, AVX, and SSE in the process of Bitshuffle. It is implemented as a fat binary, which enables the switching of multiple vector extensions in the runtime, as shown in this code snippet. Next, I'd like to present the result of benchmarks. Throughout this summer, I have done various benchmarks, including compression ratio and decompression speed for key tree or RNA tuple, and about compression time, more detailed analysis, and Bitshuffle for the standard. I'll explain them one by one. This is the result of benchmarks of key tree for nano AOD file. In this figure, horizontal axis means decompression time, and the vertical axis means compressed size. So the best algorithm will locate at the bottom left side. Also, the points refers to the result of different algorithms and levels. Red is ZIP, green is LZ4, yellow is our proposed LZ4PS, and black is the standard. To look at the yellow points, we got very optimistic result for LZ4PS. LZ4PS is better than LZ4, the green one, both in size and speed. And we can say that LZ4PS is the best algorithms among all for this file. I have done the same test for other files. This is the result for IRIS-HEP file. LZ4PS was better than LZ4 in terms of compression ratio, but it's not the case with the compression time. Also, this is the result for Atlas file. This file is known to have a bad performance in LZ4. Unfortunately, in this case, LZ4PS compressed better than LZ4 only a little, and the compression speed was not good very much. For your information, there is another compression algorithm, LZMA, and these are the result of 3 benchmarks that I showed now with blue LZMA. LZMA gets the best compression ratio, but the worst decompression speed for every file. To summarize the result, LZ4PS worked very well for nano AOD file. It got a better compression ratio than other algorithms except for LZMA, and it showed 6 times better compression speed than LZMA. But it didn't perform very much with LHCb or Atlas files. We may need more investigation about it in order to explain this behavior. Next, I've done benchmarks with RNA tuple files. This is the result for Atlas file in RNA tuple format. The graph on the left is about the file size, and LZ4PS was about 10% smaller than LZ4, which is not small very much compared with other algorithms, but about the compression speed, the graph on the right. LZ4PS was the best one, improved from LZ4 by about 6%. This is the same benchmark for H1 file in RNA tuple format. It got improved compression ratio only a little, and the compression speed is about 2 times longer than LZ4. Although it is still competitive compared with other algorithms, it didn't work that much like Atlas file. Also, for RNA tuple 2, we may need to test with other files to understand more about Bitshuffle. Next, a benchmark about compression time. As I said before, LZ4PS requires extra computation other than LZ4, and the compression speed can become bad. However, as shown in this table, the time required in compressing files with LZ4PS was at most about 30% longer than with LZ4, which I think is reasonable considering the big improvement in the compression ratio with LZ4PS. Also, to investigate more about Bitshuffle, I compared the size of each branch in T3 file with LZ4 and LZ4PS and found these things. Firstly, branches that consist only of small and positive int values have great compression ratio in LZ4PS. I think it is because there are many consecutive zeros after transposing such data. Also, float and bool values tend to have worse compression ratio than int values in LZ4PS, possibly because adjacent bytes are unlikely to correlate for such data types. As shown in these histograms, small and positive int values have good compression ratio in LZ4. The left branch consists of many big integers and did not get improvement with Bitshuffle at all. However, the right one consists of small int values and got very good improvement with Bitshuffle. Moreover, float and bool values have relatively bad compression ratio in LZ4PS. This table shows the total size of each data type for nano-LD file. Int values became smaller by more than 60%, but float and bool improved only by about 20%. Finally, I tested Bitshuffle with another compression algorithm, the standard, but it didn't make much difference. As shown in this table, even in the best scenario, Bitshuffle improved compressor size only by about 5%, which is very tiny improvement considering the result of LZ4 with Bitshuffle. So to summarize my work, I have integrated Bitshuffle into the file system of root and got promising results for some files. However, we need more investigation in order to fully understand the behavior of Bitshuffle. I have written a blog post as a GSoC report. Please take a look on it about my blog if you get interested about my project. Finally, I am truly grateful to my mentors, Oksana, Brian, Ken, and other root community members for helping me delivering this project. That's all. Thank you very much for listening.
Keisuke, wonderful presentation. Thank you so much.
Thank you.
Some questions?
I had one, maybe more for Oksana, I don't know. So the conclusion that there's a very different behavior for ints and floats is pretty interesting. Root does, I guess root knows what it's compressing. Is it conceivable to use a different compression algorithm for by basket?
Exactly. So this is actually this project and also a project that is doing Eric. I think it's like something that I would like to understand and collect information. It looks like probably will be the best to use for different baskets, different compression algorithms, and try to tune depending on the basically some heuristic algorithm that will decide if this branch is the best for this algorithm. And yeah, so there is some.
How do you deal with backward compatibility?
Brian implemented some long time ago. It calls TIO features, which is allowing you to basically to enable it to enable new features without hurting backward compatibility, because you can how to say, checking out which TIO features is enabled, you know basically if it is back compatible or not. And some experiments could decide to enable by itself. So yeah, there is some mechanism that can help to use it. But yes, still here is just a small problem, is that, not problem, but it's something that still needs to be explained, particularly to the root team as well. Why it didn't work, for example, in the case of the Atlas open data file. So we will need to do a bit more like small investigation, looking into the branches and and trying to explain.
One other possibility is that you may want to look in the IO how the IO system represents floats, because you can represent float as a subsequent integers and recast it. So I think this would be a point where we can enhance the IO system rather than having like n different compression algorithms.
Yeah. In this case, so the problem is that LZ4 was in some moment it was even defined as a default compression algorithm for root, but there was a couple of reports which were reporting exactly this problem, that LZ4 is nice, the speed is nice, everything is nice, but in the same time it was not performing well in the terms of compression. So this could be as a nice replacement of LZ4, I will say like this. So it's not like n+1, but in the same time it has all best let's say best features from LZ4. It's just a bit slower in the terms of compression and a bit slower in terms of decompression. But anyway, for decompression, LZ4 is already super outstanding comparing to all other algorithms. So it could be a nice balance. Yeah, it's just the first step that probably before we were just adding new algorithms and checking how it works. And now this summer, there's 2 students, Keisuke and Eric, which are working actually on checking out exactly what is happening on the branch level and on the like basket level as well. Yeah.
Yeah, I wanted to ask Keisuke, thanks for your work. I've seen some of your code landing in root bench. So did you land all of those benchmarks that you used in the plots in root bench or any place else?
All the benchmarks was done with root bench.
Okay, so everything there exists. Okay, good.
Yeah.
Thank you.
Okay, let's go on to the next talk. So
yes, Vaibhav is our Google Summer Code student that was busy with C++ modules on Windows, and he will report your progress, his progress.
Hello, everyone. Okay, so good evening, everyone, and good afternoon, good morning for everyone in different time zones. My name is Vaibhav Garg, and I did the project enabling of modules on Windows as part of the Google Summer of Code 20. So for those of you who do not know what root is, so root is a modular scientific software toolkit. It provides the functionalities needed to deal with big data processing, statistical analysis, visualization, and storage. It is a core software used in high energy physics, and not only for data analysis, but also as a backend for CMSs as well. And now what modules are? So any software is built using libraries which are consisting of system libraries and third-party libraries. And in C-type languages, we access those libraries currently using the hash include preprocessor mechanism. And modules provide an alternate simple way to access those libraries. There are certain problems that are inherent to the C way of using the API of a library that module fix, and also they provide better compile time scalability. I'll discuss the problems now. So what are the problems with hash include? So every time you must have included a header in a C program, we need to pass its contents with the existing code. And suppose you have a project which has M translation units, which means M C++ file, and each includes n header files. So what compiler will do is include all of those header files textually and then parse the whole C++ file as a unit. So this makes the compiler do a M cross n level of work, which is not very scalable. And this becomes even worse in C++, as there is support for templates and a huge amount of code is stored in each of the header files. Also, the hash include mechanism is fragile, as so I have to say, because those are textual inclusions of a header file. So if you have written some code prior to including a header file, that earlier code will get subject to the code macro defined in the new header file. And if it collides, then the failures happen. So there are several workarounds possible with this, and we currently use include guard, which is we use long underscore names to protect the macro of an header file, but modules give away past that. And there's tool confusion because in a C-based language such as C, C++, or Objective-C, it is very hard to develop tools because you do not know when the boundary of C finishes and C++ starts. And some libraries have a particular order of including defined, so which is not very clear by just looking at. These are some of the problems which are currently with the hash include mechanism. So how do modules solve these issues? So modules follow the strategy of semantic importation of the API of the library. So instead of using hash include that we earlier used, we use an import statement such as import standard.io, which will include all the API of the IO of the standard library. So this now replaces the textual preprocessor inclusion model with a more robust semantic model. And from the user perspective, there is only a slight change because and the identities, but the import declaration behaves quite differently. And there is currently backwards compatibility provided in root, so you do not need to change your code from the user side. Whenever a compiler will see that there is a hash include statement, it will convert it into an import statement of the similar kind. So whenever so what happens in modules is each of the header files is compiled as a separate unit in its binary representation, and whenever you load the module, you load the header file, its binary representation is loaded. So each header file needs to be passed only once. If you even included it in projects, the binary representation will get loaded instead of the textual inclusion which used to happen earlier. So what are the benefits? Earlier, if you would have noticed, there is a n cross n level of compilation happening by compiling a project of n header files. Now each of these units will get compiled only once, and we can reuse their binary format as and when required. So this leads to an O of m plus n level of work, which is easily scalable. And each module is carved as a standalone entity. So you do not have to worry about how it affects the earlier macro and change your code accordingly. And you do not need those include guards which were present earlier. And module describe the API of software libraries. Therefore, when you build tools, you can rely on that definition of the library that the module provides without worrying about any other include order that you used to earlier. So what is the state of C++ modules in root already? So in version 6.16, there was a preview of the modules technology. And starting from version 6.20 in Unix and 6.22 in OS X, out of last release, we are shipping C++ modules as default on root. This project aimed to extend the support of C++ modules of root to Windows. So why is exactly Windows different? Why can't we use the same existing code that we use for Unix and OS X? So the difference is in the compilation strategy, because Windows uses the Microsoft Visual C++ compiler chain instead of the commonly used GCC in Unix-based system. And what MFCC have done is it has removed the absence of C99 support and have employed custom functions for that you do not miss on functionality, but what changes if the structure of header files changes across directories. So we can't just use the earlier model of inclusion. So there are several GCC specific headers such as bits allocator that are not present in MFCC that we need deal with. Also, there are several invalid construction class templates that Clang has historically rejected. Clang is used in our root compiler. So there are several constructs which they have rejected, but MFCC allows. So they have introduced issue of feature of late template passing, which deals with it, but it is not very perfect, so it causes problems from time to time. So what major changes that I had to do for making module work with Windows? I had to make new module map file for standard library of Windows. So what are these module map files? So each header is, there is a file which includes the information of all the headers present in the module and the corresponding module name. So they describe how a collection of existing headers maps into the logical function of the module. So whenever we load the code, we can map it efficiently and load the particular module. So these module map files are dependent on the directory structure of the actual files on the system. As Windows uses MFCC and Unix uses GCC, there were different structure of libraries, and therefore we had to make new different module map files. And the new module map files are now closely related to the actual structure of libraries present in Microsoft Visual Compiler 3, Visual C++ Compiler 3. Now, another major change that I had to make was merging two declarations successfully when inheritable attributes are present. For those of you who know how compiler functions, we create a abstract syntax tree in which there is information about various declarations that you make throughout the program, and there are and those declarations can be made from time to time from a program. They should be readily accessible with all its properties. So there are certain attributes of a declaration that are need to be present in the redeclaration chain. And this is done using AFT reading in Clang, but somehow in the case of inheritable attributes, such a re-establishment of invariants was not there. Therefore, I had to submit a patch to Clang, which was backported to root in order to fix this issue. And then I had to make a change in which the late pass templates are not being properly passed while using the root. So what happened was, suppose each module has several template instantiations which are known as late pass templates in Clang. Now each of it has a declarer ID which is of two types, the local declarer ID and the global declarer ID. And in Clang, it was assumed that both of these IDs will same. So what the local declarer ID means is it is the module relative position of the instantiation, and the global declarer ID is the position of the declaration throughout the whole compilation unit in which it is being imported. So it was assumed that these two IDs are same, which in practice were not the case. And while passing those modules, we had declaration ID confusion, which broke. And this patch was submitted to Clang the fixed issue. And it is now backported to root after the GSoC period. Now, the last major change I had to make was teaching DLM to recognize symbols COF object file. Now, DLM is the dynamic library manager of root, which handles all the symbol lookup of root. COF object file is a format for storing the symbol which is used in Windows specific systems. Now, all the symbols that are present in the COF object file were not understood by the dynamic library manager. So we had to teach dynamic library manager to understand the symbols present in the cause object files. Okay, so there were several other changes that were made in root related to small bugs driven in the code wave or incompatibility of Unix or the MS Microsoft based system. They were fixed from time to time and were appropriately handled. So what results we get? We are now able to successfully build root on Windows with C++ modules enabled. And 65% of the tests are currently passing. And there are some minor issues that are needed to be fixed in order to make modules default on Windows. So what are those issues? I'll discuss them briefly. So with the Jenkins build system, there is an issue. As two of those nodes available with us are not able to build with the modules build of Windows. That is somehow related to the visibility of those header files, and there were only 55% tests passing currently, so we have to remove the remaining tests, and then we can make C++ modules by default on Windows. So in the end, I would like to thank my mentors Vasil and Bertrand who helped me throughout the project, and they provided immense support to me, and all other members of the root team who reviewed my code from time to time in the pull request. Any question?
I have a question. I wanted to ask, since you managed successfully to compile root with modules and Windows, did you manage to have some measurements, like to check out modules versus built without modules, and for example, if runtime was improved or memory was not improved?
Actually, the issue was because in the build system, we experienced some problems of the header file not being able to be properly visible. So I could not make the performance measurements right now.
Okay. No worries. I was just curious, maybe you had something, and it will be super interesting to see. Okay, then looking forward.
Well, in addition, the tools there for measuring memory and these kind of things are not as straightforward as what you would get on Unix. So it's a bit of a challenge.
I see.
Okay, if there are not any more questions, I just wanted to thank once again Vaibhav. He did a great job, to be honest. As a start, the total benefit of that project when I wrote the initial project was actually to manage to build the core modules for Visual Studio. That's like 2 modules. And the fact that he manages to build like 99% of the modules for root and run tests is just amazing for me. I'm really looking forward to seeing the old test passing, and as he said, we're there. So we need a little bit more work. So thanks again, and it was a pleasure to work with you this summer.
Thank you.
Well, thanks. Henry, I think you're next then.
Okay. So we'll be hearing from Nino. He worked on the Hist project over the summer. As you might know, the boost-histogram project was been going for about a year or so now, and that was always designed to have a front end for analysts. And so Nino managed to work on that to get quite a bit together to 4 major new features in, and we'll be doing a full 2.0 release probably in about a week or so of that work.
Hello everyone. This is Shuo, and you can call me Nino. In this summer, I'm working on building a histogramming tool for high energy physics, which is part of the HEP project in IRIS-HEP. Then let me give you a brief introduction about my work. The HEP is a community-driven project with the aim of providing particle physics at large with an ecosystem for data analysis in Python. One of the most amazing tools in HEP is boost-histogram, which is the Python binding for the C++14 boost-histogram library. This is the fastest library for histogramming while still providing the power of a full histogram object and supporting various types of histogramming manipulations. You can see the new features of boost-histogram on its website. Based on boost-histogram, we implemented an analysis-friendly package, Hist built on top of boost-histogram, and provided commonly expected histogram features. This package allowed a wider range of dependencies and features that are not admissible in the core package, and it can be installed from pipe or conda. For example, you can simply use our package like the code snippet on the left, and you'll get the visualization result like the red parts according to the property of the histograms. For example, this is the visualization result of a 1D histogram, and this is a 2D histogram. And these are the SVG wrapper for different histograms. Next, I'm going to show the new features of Hist in more detail by showing you a notebook. Considering that it takes some time to build the demo notebook on Binder, so I just run it locally here. For you, you can run the demo notebook on the Binder by clicking this button. Okay, before showing how the new features work, I need to clarify the relationship and differences between both histogram and Hist. The boost-histogram library should be viewed like NumPy, a powerful fundamental library for supporting histograms. However, it has no dependencies and is designed to be exact. It means to be usable as a backend for other histogramming libraries. Like Pandas provides a nice interface to NumPy that added columns, plotting adapter, and more. Hist is an analysis-friendly front-end to the boost-histograms. The difference of them are shown as below in this table. Generally, if a feature doesn't add dependencies and is useful, it may be upstream to boost-histogram. Currently, Hist provides 4 things that boost-histogram doesn't have: names, UHI, plotting, and quick constructors. Let's take a closer look at them through some code snippets. Hist assigns meanings to the metadata via names and labels. Access in Hist can have a name and a label. The name is special, it needs to be unique to a histogram, and it's completely optional. You can even mix named and unnamed access. A name can be used to identify an access anywhere. An index can be used. For example, here we construct a Hist instance with the name of X and Y. Then we can fill it via their names. And then we can use matplotlib HEP to plot it. Note that matplotlib is also used for 12 in HEP. Okay. Furthermore, we can also use names to access the contents and modify the labels at any time. Note that as the name is the only identifier to the axis, so they cannot be changed after created, and they are unique. If you love names, there is even an experimental named Hist that enforces only named axes. You can't use normal position axes on named Hist. The second important feature I want to show is UHI, which stands for Unified Histogram Indexing. Hist supports an experimental UHI addition that allows for ultra-terse UHI. You can perform all manipulations directly inline without extra imports. Well, the rules for single beam or slice endpoints is you can use a non-negative number such as 3 to access the contents as being coordinate 3. And you can use a complex number such as 1.5G to access the contents as data coordinate 1.5. Similarly, for string category access, you can use strings to access directly. There are also some action slots. For example, you can use some just like you did in Python building grammar. And you can also use complex to represent the shrink scale to rebind the axis. Let's see an interesting example here. First, we use a Python icon to create the hit probability data as X and Y and fill them into a histogram named PY. Then we can plot it. And we can also zoom it in. We can also rebin, and as you can see, it becomes brighter because more hits will fill in the bin. The same principle applies to string category. And here we have a histogram with 3 bins, A, B, and C. And we can access the A bin and A 2-3 bins. I assume you must be interested as a plot above. Yep, we use our own plotting methods, and there are also amazing new features of Hist. The plot method will automatically give you a plot according to the dimension of the histogram. In this case, we have a 2D histogram, so we can get color mesh. And if the histogram is 1D, you will get a line. If you want to get the projection of a 2D histogram, you usually use dot-plot 2D _4, and you can also use your customized keywords. Here we have CMAP for the main plot and LastDL for the top plot, etc. In the end, I would like to introduce his quick construction system. You don't need to use his namespace everywhere like you do in boost-histogram. He supports a very experimental quick construction system. You can create and transform a histogram like this, and you can also you can even specify the storage. For example, Hist regular axis 10 bins from -3 to 3, and in storage of int 64, fill with X data. Oh, sorry. Note that you cannot give storage or access to an existing histogram like this. Say if we add new access to this existing histogram, an error will be thrown. Yeah, a runtime error cannot add an access to existing histogram. Okay, I think we can get back to the PDF for now. To sum up, Hist enhances the boost histogram in all parts of the left circle of histogram. Hist allows users to serialize and deserialize both the histogram from root and pickle format and make sure CK-HEP 12 to community well. Hist also provides a more convenient method for initialize histogram. You can use Hist storage and transform proxy for quick initialization. Moreover, 2 types of histogram are given for different usage. Hist is the general one, and named Hist is the name-oriented. Hist gives users more choices to do some manipulations. User can use access names to fill, project, and access. Plus, complex numbers are also allowed in Hist to access bins. Some of the functions of Hist facilitate several statistic trials in CPI and image analysis data. Hist offers amazing visualization tools to show the histograms of 1 or 2 dimensions. Furthermore, SVG wrapper format is allowed in Hist. If you want to know more about them, you can refer to our documentation. Here, Hist reads the doc there. We provided some resources on this page to help you better understand this 12, most of which are used for CK-HEP 12s. In the end, I want to say, currently we have very few users, but some people have helped us to find bugs and give us useful suggestions. We are looking forward to your contributions and cherish your efforts. Hope you can join us. So Google Summer of Code is ended. I will still keep track on this project and contribute to it. A new version of Hist is around the corner and could be published in this week, hopefully. Thanks for your listening. Any questions?
Thanks for your talk. I think I had one, but I lost track of what it was. You were giving an example of not being able to alter that one there, not being able to alter the existing histograms, and that's I guess I didn't fully understand that. There's essentially a global. Is the way this works? There's a global list of Hist objects, effectively.
Yep.
Okay.
Here we create a histogram object. We have filled it with data X. It's NumPy normal array, and so we cannot give a new access to this existing histogram because if so, we need to fill 2D data. If we want to create a 2D histogram, the correct usage is like this. Fill X and Y.
Oh, I see. I misunderstood. That makes sense. Yep.
Yeah.
Okay. Thank you. Anyone else have questions? I thought it was a nice presentation. Looks like there aren't. Okay, I think then we're done. Well, okay. So thanks everyone for joining, and definitely all 3 presenters for your work this summer. I think it looks like we had 3 successful projects here, so that's really great. Okay, thanks everyone.
Thank you too.
Bye.